All right, so if you picked up the packet before we left for our e-learning hiatus, it says we have a list for week 1 of boot camp, but obviously that has completely changed, so you can cross that out. We do have this nice list of expectations, so if you have the packet, you can read through all of these. If you don't, you might want to pause the video and look at all of these things, so you could do that now if you need to. But we are going to jump in with our first review topic, which is going over limits. And when we first talked about limits, remember we can find a limit at as x approaches a certain value, and we do that with direct substitution, or we can find limits at infinity, and that's where you want to deal with top heavy, bottom heavy, etc. But we're going to focus today about limits approaching some value, we'll call it a. Okay, so when we want to figure out, let's say the limit as x goes to 3, the first thing you want to try is direct substitution. And direct substitution will lead you to a variety of things. Direct substitution might lead you to a number, might lead you to a number over a number, might lead you to 0, might lead you to 0 over a number. All of these are fine, those are just your answers. Sometimes direct substitution will lead you to a number over 0, and this we would say the limit does not exist, because that means that you've hit some sort of a vertical asymptote. So from the right or from the left, your function might run up to infinity or down to negative infinity. But overall, we can say the limit does not exist because we're not approaching a finite value. We're approaching an infinite value. And then remember, we get that last situation where you might get 0 over 0, and that's where you have to keep going. And some ways that you could keep going are with algebra, so expanding expressions out or factoring. We could use a conjugate. We're going to use that when we have a square root involved. You might have to deal with double fractions. There could be some denominator work that you can do, and sometimes trig. But basically what you're going to try to do is to get a term to cancel with the numerator and the denominator so that your a is no longer a problem spot, right? Because this means you've encountered some sort of a hole in your graph. We also can use a graph itself. And remember, graphs, if they are provided by the AP exam, are great to use. Graphs, if they're on your calculator, are okay. And graphs, when you have to draw them by hand, are sketchy. I would not rely on them. And then the last thing would be to make a table. But we are calculus students, and so we know that making a table, even if you get quote unquote close to your a value, you still are super far away. And so a table is not very efficient in terms of finding a limit. So as a nice review, again, if you have the packet, you have all of these ready to go. If you don't, you can take a second in your notebook paper to work on these, or you could print the packet if you would like. But I'm going to have you pause the video. This is intentionally part of the timing of the lesson. We're going to give you about 10 to 15 minutes to be able to do these 7 limits. So you're going to pause your video, you're going to work for a while, you're going to come back and check my answer key. I'm not really going to explain much about them, but I will show all of my work. So go ahead and pause, try them for yourself, try every single one, and then come back and check the video. All right, so here's our limit answers. The first one should have come out to -1/7. You can pause the video and look at the work if you need to. Second one should come out to -12. Again, pause if you need to. The third one requires no work because we got a number over 0, so it does not exist. This next one, we've got double denominators. I got an answer of -1/9. Again, you can pause the video and check my work. I chose to clear out my denominator, so I chose 3 and x plus 3, so that when I distribute this in to this first term, the x plus 3's drop out and I just have 3, whereas this one, when I multiply in, the 3's drop out and I have x plus 3. Then whatever you do to the numerator, had to do to the denominator, so I left that there, and then stuff eventually cancels. So you can pause and look at that one. These next two both require multiplying by a conjugate, so I'm going to leave this slide as this, so you could pause it and write down anything that you need to. But I came up with -5/8 and then 1. Okay, so you can go through and look. I tried to do a little bit of coloring so you could see how stuff got introduced. And then finally, this one I want to actually talk through. It says, what does this look like in calculus? Well, this looks like the same structure as the limit as x goes to a of f of x minus f of a over x minus a, because remember this is just old school slope. This is closing in the secant slope to become the tangent slope. So what I need to pull out is, what is my important information? Well, my f of x is sine x, and my a value is pi over 6, and this is equal to the structure of f prime of a. So I need f prime of a, which means I need the derivative of sine, which is cosine, evaluated at a. The cosine of pi over 6 is the square root of 3 over 2. All right, so using our limit definition to recognize that that really is just writing the derivative. Okay, so today's lesson, the new part, is something called L'Hopital's rule. And sometimes you'll see it as L'Hopital spelled like this. Sometimes you'll see it as with an S, like the hospital. Okay, so that's why I've got our big red cross going on over here. My Calc 2 professor used to call it L'Hopital's rule. So L'Hopital's rule is a rule that says if f and g are differentiable, so we have the ability to take their derivatives, and g prime is not equal to 0, okay, if we are looking for the limit as x goes to a of a function over a function, and we end up with 0 over 0, where we're used to keep going, or any form of all these infinities over infinities, which is really like when you have the functions that are racing each other, right? We don't know where they're going. Then the limit as x goes to a of f of x over g of x is equal to the limit as x goes to a of the rate of change of f compared with the rate of change of g. Okay, something to note, in your packet it already has it, but this is not the quotient rule. Okay, so this is a shortcut for evaluating limits. So what I would do is I would go back to your first page and add in here L'Hopital's rule. Okay, so if we can use L'Hopital's rule, then we should. Okay, and we'll talk about a couple examples of how you know, but L'Hopital's rule can only be used if we have the indeterminate form of 0 over 0 or infinity over infinity. Okay, so everyone asks, well, why didn't we learn this earlier? Well, the thing is, L'Hopital's rule requires derivatives, and we didn't know derivatives earlier. So here's a proof of how this works. F prime of a over g prime of a. Hopefully we can all get behind this argument. This is our limit definition for the derivative of f. This is our limit definition for the derivative of g. Well, because this is one whole limit, we can rewrite it as such. When you divide two fractions, you really are going to multiply by the reciprocals. So x minus a over g of x minus g of a. So our x minus a's cancel out. So that's where I am at this line. But then we said this only works if our limit was going to 0 over 0, which it does, right? The limit as x goes to a of f of a over g of a, we're going to end up with 0 over 0. So we get right back to our limit as x goes to a of f of x over g of x. So this whole thing, these are going to be equal. All right, so again, L'Hopital's rule can be used to evaluate 0 over 0, but also infinity over infinity. These are the two that AB uses, all right? You might see your BC friends working with these indeterminate forms, right? Because like, what is infinity times 0? What is infinity minus infinity? Students often say 0, but think about infinite numbers between 1 and 2, infinite numbers between 1 and 5. Isn't this a bigger infinity? Weird. 1 to the anything is supposed to be 1, but to infinity? Are we sure? 0 to the 0? Unsure. Infinity to the 0? I mean, there's so many different things, right? We don't know what these are. So we can do L'Hopital's rule if we change them to be in one of these indeterminate forms. But again, that's above our pay grade. That's a Calc 2 thing. We're going to focus only on if we end up with 0 over 0 and we're supposed to keep going, or infinity over infinity, and we would need to keep going. I'm going to let you pause this to read it. So go ahead and pause. Okay, so what we're really doing again is we're going to compare the rate of change to the rate of change for each function to see which one is kind of impacting that limit more. So it says apply L'Hopital's rule with proper notation when possible. So I'm going to show you a proper notation one. I'm going to move, oh, I can't move that down, just kidding. So proper notation, you have to show the AP reader that you are in fact getting to something where L'Hopital can be used. So the limit as x goes to -3, we already did this problem. We know the top is going to go to 0. We know the bottom is going to go to 0. And then what you want to tell them is that this is indeterminate. Okay, so we're not going to write keep going. That's just a Schwartz thing. Indeterminate. And so we're going to say by L'Hopital's rule, this will be equal to the limit as x goes to -3. If I take the derivative of the top, it's just going to be 1. If I take the derivative of the bottom, it's going to be 2x minus 1. And this limit is not indeterminate. This limit ends up being 1 over -7, which is what we had for our first answer. This next one, as x goes to 2, this is going to 6, and this is going to 0. So remember, this limit just doesn't exist. We can't use L'Hopital's rule there. We already had our answer. It's only when we have an indeterminate form that we get to use L'Hopital. The limit as x goes to 4, we know from our previous example, this is going to go to 0 and this is going to go to 0. So again, we're going to say this is indeterminate. So by L'Hopital, this whole thing will be equal to the limit as x goes to 4. I'm going to take the derivative of the top, 1 minus, this is going to require a chain rule. So you can see sometimes the derivative is not all that friendly. So you can pick and choose. Would you rather just multiply by a conjugate? Maybe. And then this is going to be over -1. So now when I plug in 4, this is going to be 1 minus, 3 times 4 is 12, plus 4 is 16. Take a square root is 4. Put it on the bottom is 1/4. That'll be 1/8 times 3. So this is minus 3/8 over -1. And remember, on a free response, that could be your answer. Okay? But also 1 minus 3/8 is 5/8. Divided by -1 is -5/8, which is the answer that we got with all that conjugate work that we were doing before. Last one, right? This limit, if I try to just plug in pi over 6, direct substitution leads me to 0 over 0. So this is indeterminate. Of course, I'd still like for you to do this one using the limit definition of the derivative, but that's okay. This is indeterminate. So by L'Hopital's rule, this whole thing will be equal to the limit as x goes to pi over 6. The derivative of the top is cosine. The derivative of the bottom is 1. So direct substitution would say the cosine of pi over 6, which is the square root of 3 over 2. Okay, so again, L'Hopital's rule, there's no slide there. L'Hopital's rule can be used when we have 0 over 0 or infinity over infinity. All right, those are going to be our indeterminate forms. And then you want to tell the AP reader that you are using L'Hopital's rule, which is where you compare the rates of change. So the rate of change in red for the numerator, the rate of change in green for the denominator. And I'll leave this slide up so you can press pause and copy anything down that you need to. This structure is super important. The 0 over 0, showing them that the limits, right? This can't ever be equal to 0 over 0. We've never written equals. We've just said that this is indeterminate. It's going to 0 over 0. All right, the next video, there's some multiple choice for you to practice in your packet, and there's a video that goes through there from Mr. Lakin. So you can watch that and continue on. That's your practice for today. There is no AP classroom.